Okay, so let's start our today's session. It's a pleasure to begin the session 105 of our EDP and Applied Mathematics seminar. Today, we are pleased of having two great Spanish mathematicians, Maria Luisa Rapun and Luis Vega. The first speaker will be Maria Luisa Rapun. She is currently professor of the Polytechnic University of Madrid in the Department of Applied Mathematics to Aerospace Engineering. She has a degree and PhD in mathematics from the University of Zaragoza in Spain. She has worked in several Spanish universities, University of Zaragoza, the Public University of Navarra, the Complutense and the Complutense of Madrid. Her main lines of research are the design and analysis of numerical methods for the identification and characterization of defects in damaged materials and the design of reduced model with application to aeronautical engineering. So today she will give a talk entitled Non-Invasive Imaging Using Numerical Techniques based on Topological Derivatives. So thank you very much, Maria Luisa, for accepting to give a talk in our seminar, and you can start.
Okay. So thank you very much. Thank you for the invitation. It's a big pleasure to have the opportunity to share my work with you. And I thought that since this is somehow a general seminar on partial differential equation and applied mathematics, I'm going just to give an overview about my work without entering into much details about theorems or the proofs. Okay, so and my talk is going to be about non-invasive imaging. So this means that we are going to perform non-destructive testing to try to identify some objects. So let me start by introducing the kind of inverse problems we want to solve. So imagine that we have some medium, which will be called R in my notation, with some obstacles inside. And the objective is to identify how many objects we have, how big they are, where are they located, and so on. So as presenting it as such a general problem, you can think in many, many applications. For instance, you can think that we are thinking in medicine applications and you want to look for tumoral clots, or in your physical applications, looking for antipersonnel landmines, or in material testing where you want to find some kind of damage, cracks, corrosion, and so on. Okay, for doing so, we are going to apply non-invasive or non-destructive testing, which means that we are going to interact with the medium without altering their properties. This means that we are going to generate some kind of excitation, and we will look how the medium responds to our excitation. And we are going to have some measurement that will be called in general K, which will be part of the boundary or a discrete set of points. For instance, imagine that we want to test if we have some kind of defect inside some aluminum plate. And for doing so, what we do is just to hit my plate with a lamp and then take a picture with a thermal camera. From this information, from this picture, we want to process the data to identify defects. Or in thermal or electromagnetic acoustic scattering, what we do is to produce a wave, and then this wave is going to interact with our objects and try to identify them from measurements from a reduced number of detectors. So this will be K. So in the case of thermography, it's just my picture. In the case of receptions, at some points is the set of receptors. Okay, for obtaining these objects, we are going to propose methods that are based on finding a minimum of some shape cost functionals, meaning that we are going to deal with this kind of functions which are related with we are going to measure all the contributions in our observation region K. And this function small j is something that depends on the solution u omega of a PDE problem modeling the problem we are going to solve. For instance, if we are dealing with thermography, this function u omega is the solution to a thermal problem, to the heat equation. And if we are thinking in acoustic scattering, then this function u omega solves a wave equation. Okay, and this function small j is a function that represents what can we measure. This means that, for instance, if we can measure the total wave at the receptors, then we want to minimize the difference between our measured data at the receptors and the solution to the problem where our objects are omega. But in some other situations, yes, this function j is different and depends on what we can measure. If we can measure the normal flux, then it's given by this expression, or if you can only measure the amplitude of the waves, then you have a different function. So depending on the problem, you want to minimize a different shape cost function. And of course, for solving this kind of minimization problems, you can apply many different techniques. And we are going to explore today a method based on the computation of topological derivative. But just to fix an idea, I'm going to introduce two model problems. The first one is the acoustic scattering problem that I already said. So we are going to produce some kind of incident wave. In particular, we can think in a planar incident wave, which is given in a direction d, and kappa is the wave number. And then the solution to my forward problem, to the total field that we will measure when my objects are omega, then will be a solution to this PDE problem. We have the Helmholtz equation because we are thinking in time harmonic excitation. We have here the wave number kappa. This means that we are dealing with sound hard objects, and this condition here is a condition that says that my waves propagate, but they don't come back from infinity. Okay, then in this case, you can measure. Your data will be the measurements at some receptors at the points here marked by red, and then you want to minimize this cost functional. So we are comparing the solution to our forward problem with the objects are omega. We want to determine these objects omega with the solution to our measurements. So this is the data. This is the way this function depends on the objects we want to obtain. Okay. In case of electromagnetic scattering, we will have a different PDE problem, which is going to model how the electromagnetic waves propagate. So now we can generate incident waves, which looks like this expression here, and we will measure the total electric field at my receptors. Then the cost functional looks rather similar, but now these functions are three-dimensional functions and are the solution of a PDE problem modeled by the Maxwell equation. Okay, so depending on the problem, we have a different PDE problem behind. And for computing the minimum of this function to identify the regions that contain objects, we are going to use this topological derivative. So let me introduce first this concept. So imagine that we want to determine if we have some defect in some region R. And for doing so, we are going to use a scalar function d, which is the topological derivative, which is defined as follows. So for each point x belonging to our region, we are going to consider a small ball of radius epsilon. Then what we do is to compare the value of the functional when we introduce this very small object with the value of the functional without any perturbation. Of course, since my ball is very small, this difference is also small. So if you perform a syntactic expansion of this difference in the numerator, then you can see how this behaves in comparison with epsilon. Then the topological derivative is defined as the limit when epsilon goes to 0 of this difference divided by some positive function f, which is selected after looking at this difference in such a way that this limit exists, does not vanish. This means that it's not equal to 0 everywhere, and tends to 0 as epsilon goes to 0. Usually this looks strange, but this is usually this function is nothing but the measure of the ball. Okay. Okay, then if you look again to the definition, you can see that for each point x, we are going to have a scalar number, a real number, and this number measures the sensitivity to introducing this small ball. And the points at which this topological derivative attains large negative values will be identified as points that belong to the defects. Maybe this is more clear if we write this definition in this equivalent form like an asymptotic expansion. So if we remove here the limit from the definition multiplied by f, you write it as an expansion that says that the value of the cost functional when we introduce this small perturbation at the point x is equal to the value of the functional without any perturbation plus this first order term. This means that if we look at this term, since the function f is positive, if the point x is one at which this topological derivative is large and negative, then this quantity here in red is also negative, and this means that the functional is decreasing. Recall that we are interested in the points that are a minimizer of this functional. Okay, so the strategy for identifying damage region is nothing but evaluating the topological derivative at a grid of points. So imagine that we are in a scattering problem, we are producing our incident wave, we have our observation, and we want to determine if there is some defect inside this region in blue. Then what we are going to do is to consider a grid of points of this region, and we are going to evaluate the topological derivative at all these points. Then we will consider as our damage region the set of all points at which this topological derivative is large and negative. And the concept of large and negative will be defined in terms of the minimum value of the topological derivative by considering some constant value here. I will come back later to this definition, but basically we just want to evaluate this function, and you want to determine the points at which this derivative is large and negative. But of course, if we look at the definition, it seems not to be very practical from the implementational point of view. So if you want to evaluate this with a computer, we need an expression which is more easy to implement. So in practice, we are not going to use the formal definition. We are going to work with this definition to find a closed form expression, something that you can evaluate and that you can implement with a computer. Okay, and for doing so, we are going to use an equivalent definition of this topological derivative as a limit of shape derivatives and performing some asymptotic expansion. So this is the more technical part. I'm going to skip all these details, just a few words about how to obtain a formula. And the way is as follows. So if you want to evaluate the topological derivative at a point x from the region, we take a ball of radius epsilon and then define a vector field which is equal to the normal vector at the boundary of the ball. And then you extend this vector field at the remaining of the space such that this function is equal to 0 when you are not close to the boundary. Then the next step is to consider your region without the ball and the transformation of this region when you perturb it in the direction of this function b. Then you get a function when you evaluate the cost functional at this perturbed region. We have a scalar function that depends on this parameter tau. Then you can compute the shape derivative, which is the derivative with respect to this parameter tau when the value of tau is equal to 0. And finally, the topological derivative can be computed as a limit of shape derivatives. Okay. And in the intermediate steps, you get a formula for the shape derivative that, of course, depends on epsilon. And then what you do is to compute this limit. And here is the point where you select the function f. Okay, so this is the technical part. Depending on the problem, you have a different function j here, and you have to compute a different shape derivative. But in the end, what you want is to identify some closed form formula. So I'm just going to show you how this formula looks for our model problems. For instance, in the case of the acoustic wave propagation, the formula that you get is really, really simple. You can see here how it looks. It's defined in terms of the solution U of a problem without any object, meaning that if you have any object and you generate an incident wave, then what you are going to measure is exactly the incident wave, so you know the function in closed form. And this function that will be is the solution to an adjoint problem. That, in this case, is known in closed form. So what you need to evaluate is very simple. This very simple expression, which involves a linear combination of green functions, which are the solution to the which are the green function for the Halford equation, which in the case of the two-dimensional problem is given by the Hankel function of the first kind and order 0, and in the three-dimensional case is given by this exponential function. Okay, so in the end, what I want to emphasize is that after this complicated computation, you get a very simple formula. So at the point x, I'm going to evaluate this function uinf, which is given in closed form, and also this function winth, which is also known in closed form, and the inner product of these gradients, which is also known in closed form. So in practice, implementing the topological derivative and evaluating the topological derivative is very, very simple. It's just a few lines in a MATLAB code. So the reconstruction will be almost for free. We only need to evaluate this function, and just also to emphasize that the real data, the data that we measure at the receptor, is introduced in the formula by means of these values that appear here. We need to know our measurements at all the receptors, and we need to evaluate the incident wave at the receptors. Okay, so let me show you some numerical experiment for this case. So in this example, my objective was to identify this object, which boundary is given here by this black line. So it's a kind of potato. And what we did was to excite the medium from 12 different incident directions and measure the total wave at all these observation points. Then, by computing the topological derivative, this means by evaluating this expression here at agreed points, I obtain this color map, this picture here in which the largest negative values are given by blue colors. So if you look at the darkest blue colors, you can see that all are concentrated inside my object, meaning that I'm finding a region which is inside the object. So you get from here a reconstruction just by keeping, for instance, all the largest blue color, or just you increase the size if you keep a larger percentage of negative values. Okay, this is controlled by the constant C0 I introduced before. Okay, in the case of electromagnetic waves, you can also derive a closed form formula, which is very, very simple to implement. In this case, it contains two different functions. This function uinf, which is the known incident field, in this case is given by this function here, and the solution to the adjoint problem is also known in closed form and is given by the green function for the Maxwell system. Okay, so let me show you how the method also works in this electromagnetic scattering problem. So in this case, we want to identify some objects that are inside this cube. For doing that, I'm going to evaluate the topological derivative at some different planes contained in this cube to try to identify my true objects, which are these two different objects here. Okay, in this case, I generate many different incident excitation from all these arrows, and my measurements were taken on the blue crosses. So I'm going to show you now a picture where I'm going to visualize the values of the topological derivative at different planes. Some planes of the form x equal constant, y equal constant, and z equal constant. And as before, the largest negative values will correspond with the regions which are identified as belonging to some object. Okay, so let me open the window, the movie. Okay, so you can see that at the beginning, so in all, stop. So in all these planes that do not intersect my objects, you see only red colors, means that the topological derivative is not identifying any objects here. But at some other planes, you get some regions which are in blue color, meaning that the topological derivative is large and negative. So in these regions, it's supposed to have some object. Again, and these are the other planes. And you can see that the largest negative values, the more the darkest blue colors correspond with some interior regions to this object, which is the biggest in size. Okay, so these are some captures of my movie. And okay, from the moment I'm telling you that you need to look at the regions at which my topological derivative is large and negative, meaning that it's in blue color, but from the practical point of view, we want to identify if a point belongs or not to an object. So to define this object, I consider this approximation I introduced before. So once I compute the topological derivative, and once that I know these values, I identify the minimum, for instance, in this case is around minus 16, and then I will keep all the points at which the topological derivative is large and negative by this definition here. So I will calibrate where to cut, meaning that I'm going to keep all the blue colors or until up to green or whatever. So if I select a constant which is equal to 0.3, in this example, then my reconstruction only identifies a small region which is inside this object here. By increasing the value of this constant, then the size of my objects also increases, and my reconstruction still has only one defect, but it's bigger in size. And if I increase this constant to 0.6, you can see that my reconstruction has the correct number of defects. Also, the position is correct. The only problem is that the shape is not accurate. But you have to take into account that the method is very simple, it's not costly, it's not iterative, and I'm just producing a, let's say, a first step approximation. But this first step approximation could be very interesting from some other methods that iteratively can improve the shapes. Okay. Another way of improving shapes is just to consider data that come from different experiments. This means that in some examples in practice, you can not only produce excitement from one frequency, but you can also excite the medium at different frequencies. Then, in this case, it's interesting to combine results coming from some different experiment. So just to show you what happens depending on the frequency, the wave number is defined in terms of the excitation frequency and the velocity of the wave. You can see that, for instance, in this example, which is very close to the previous one, but now I have 4 different objects. If I evaluate the associated topological derivative at different frequencies, you get very different results. For instance, here in the first row, you can see that if I consider a small frequency, a small wave number, then the largest negative values concentrate inside the biggest object. This means that for this wave number, I can only identify probably, well, it depends on the constant, but you are going to identify the biggest 2 objects. If you increase the frequency, then your wave number also increases, and what happens is that the information that provides the topological derivative is different. Now you can see that the largest negative value concentrates inside these 2 biggest objects, but also inside the other one. And if you increase it to kappa equal 8, then the results are completely different. Now you can see that largest negative values are inside the ball, which were almost not seen here and completely missed in this other example. And also there is a difference here. Instead of being inside the biggest object, what you see is that the largest negative value are attained at the boundary of the objects. So this means that different frequencies provide different information, and it's interesting to combine all this information. So then the next idea was to combine monofrequency results just to improve shapes. And what we do for doing so is just to consider a different cost functional. Now we are going to consider a linear combination of different functionals for different frequencies with just considering some different weights here. This means that by linearity, the topological derivative is nothing but the linear combination of the individual topological derivatives. And there are many different ways to define these weights. But one possibility, which is very simple, is just to look at the results. So if you look here, the largest negative values here for the small wave number is about -2, but here is -8, and here is -20. This means that if I just add the contributions, then I'm basically going to recover only information from the largest frequencies. So what we are going to do is just to normalize all the contributions to make all the frequencies equally important, just by dividing by the minimum. So making the minimum equal to -1, and then just to add the contribution. And what you can see in the next slide is that by doing so, you get an indicator function which is very clear, and that if you keep the largest negative values, for instance, for the constant C0 equals 0.6, then you get a reconstruction which is very sharp. So we are not only recovering the correct location and the correct number of objects, but also the shapes are very accurate. Okay, so in this case, when you have information coming from different incident directions, when you have observation points everywhere, and you have data coming from different frequencies, then you can get very nice and very low computational cost. Okay, and now in this second part of the talk, I just want to give a little overview about other different problems that we have been working on. So my first problem here is related with a biological problem. Is used for doing so holographic microscope, a light microscope, in which one of the difficulties is that you can only generate waves in one direction. So you have a laser here which produces waves only in one direction. And what is also very important is that you put your sample here, you put your cells here, and you can take now an image from your camera only on a plane. So now you don't have information all around, but only on a planar wave, on a planar visualization. And what you get is what is called an hologram. So in this case, you have very limited information, not only because you can only generate waves in one direction, but also in the way you get the information. And in this case, what is also very important is that you are not only interested in determining if you have a cell or not, but it's important to determine the cell, the shape of the cell. Okay, so I want to show what happens in this case when you have this example here with two different cells, and this is the image you get. This is your hologram, the data you want to process by using the topological derivative, and compared with this other example, what if I go back and forth, you can see that the holograms are rather similar, and the difference is only here. So in the first case, you have here two cells, one cell that is going to be split into two, and here the cell has been split into two. So it's a very small perturbation which is complicated to identify. In this case, if you compute the topological derivative, with what happens is that you don't get a correct approximation. You're going to visualize what happens here. So let me go back. So the topological derivative is only able to provide an approximation which says that you have two different cells, but is completely unable to determine the shapes. What we did then was to combine this approximation with a different technique based on iteratively regularized Gauss-Newton iterations, just to improve shapes. And by doing a few iterations of this combined method, what you can see is that after a few iterations, let's see it again. Okay, I will stop here. You can see that after 15 iterations, our reconstruction is very close to the full configuration. Okay, sorry. So if you go to the other example where my cell has split into two different cells, you can see that in this case, our our initial guess, compute by using the topological derivative, has only one component, so the method was not able to determine the correct number of cells, but after a few iterations of the combined methodology, which combined regularized Hamilton method with the topological derivative, our construction was very nice. Okay. Okay, another application I want to mention today is related with real experimental data. This means that in all the previous examples, I produce my data, meaning that I selected the objects, I solve the problem to generate my data, and then I produce some noise just to simulate experimental noise. But this data was not real data. So the next step in our work was to work with real experimental data produced at, and doing so we use a database which is very nice. It's open and is published in the journal Inverse Problems, and is precisely is published for giving the opportunity to many different groups to test their favorite methods, all with the kind of the groups. And as you can see here in the journal, there is a lot of information about how the experiments were carried out in their laboratory and what kind of effects they considered. So there are some different kinds of objects, and also information about where are the receivers, where are the target located, and what frequencies were used. So this is very nice that we had at our disposal information coming from different frequencies, because we could use the multi-frequency topological derivative. And if you look at the different objects that were tested, this one, the one with a U shape, was the most complicated one, and many groups have problems to identify the correct shape. But as you can see here in my next slide, you can see that the topological derivative produced a very sharp reconstruction of the object. So we were very happy to check that the method works not only when you produce the data, but also with real experimental microwave data. Okay, and my final experiments will be related with another technique, another non-invasive technique, which is based on active thermography experiments. In this case, as I previously mentioned, what you do is to hit the structure you want to investigate, and then you take a picture with your thermal camera, which is like a normal camera, but these kind of cameras are able to capture infrared radiation, and this radiation is translated by the camera. You don't need to process it as a temperature color map. And then from this picture, you can try to identify some internal defects. This problem is much more complicated than acoustic, electromagnetic, or this kind of information, because the heat equation has a lot of diffusion, and it's very complicated to sometimes to identify small defects. For instance, in this simulation, we were taking a picture from a thermal camera of a plate made of aluminum with some internal defects. And what you can see here is that if you hit from a lamp located in this position and you take a picture, you get a color map that basically says that this part of the plate is hotter, because the lamp is located here. But the image that you get with a plate which is perfect and with a plate without defects is basically the same. If you compare these two thermograms, these two pictures, you get an image where you cannot say if there is some internal effect or not. You basically see only the noise. And this has not to do with the position of the lamp. If I change the lamp, the position, then it happens the same. So I basically can only say that this part of my plate is hotter, but I cannot say that there is an object or not inside. I cannot say if there is some crack or something inside. side. Okay, so the idea here in this work was to use the topological derivative to process this kind of data, this kind of images, to try to identify the location of the defects. And as you can see here, the method is very competitive, and by processing exactly the same data that I'm showing here, we were able to identify the position of the 6 tiny interior cracks that were located inside the plate. Okay, and just to end with the talk, I want to show you my most recent research done in this direction, which is the most complicated thing I have done so far, which is related with real thermographic data that was provided by the Center for Aeronautical Technologies. And it was related with inspection of this plate that you can see that has a strange form and has some perturbation here, so it's not a perfect plate, it's not polished in this zone. And if you look at the other side, you can see that there are some defects that were carved here. So there is a hole. So the hole, of course, you can see the hole because it's a trespassing hole, but the other defects cannot be seen when you look at this side. So we are going to take picture from this side. We are going to hit my plate from this side, and then we try to determine the position of all these defects. And for doing so, in this Center for Aeronautical Technologies, they perform some experiments where they locate here the plate, they hit the plate from these lamps, and then they capture some sequence of thermograms by the thermal camera. And the data they provide us was a sequence of thermograms. So I'm going to show you the movie they provide, okay, so you can see here what happens. So at the beginning, my plate is very, very hot, so you cannot see anything. But then after, in the next thermogram, you can almost not see nothing, but then in the next one, you can see the shape of the transversal shape of the effects. So this is how thermography usually is used. So you take you capture a sequence of thermograms, and from this information you get how are located these defects that are big enough to be identified by these thermograms. And here is just the full sequence, and you can see that after a few times, then you basically say you cannot see nothing. Okay, so this sequence is very slow here, just to show you how they look in practice. It's taking only 4 seconds. Okay, so now the problem was, okay, I have this sequence of thermograms, and I want to process them not only to identify the location. So I don't want to know only the information that thermography gives, but I want also to know how deep these defects are produced, okay? And these were the through sizes of the defects. And for doing so, the first thing we had to do was to pre-process our data. So our data contains a lot of noise, a lot of experimental noise, and we want to pre-process them to clean them up. The second difficulty we found is that we don't really know the location of the lamps. We don't know how to mathematically propose a model for the lamp heating. And if you want, and even if you know how to model them, then you need to solve non-stationary problems. So these are time-dependent problems, and the adjoint problem is going to be also a non-stationary one, meaning that you need to solve the backwards heat equation. So you need to solve the heat equation backwards, which is one of the most difficult inverse problem to solve. Okay, so to avoid all these situations, what we did was, first of all, to consider all our images and to process them in order to clean up the noise just by using the singular value decomposition method. So for doing so, we define a big matrix from these images. So each image here is just just put as a long vector. So it's the first column, the second column corresponds to the second thermogram, and we do so for all our images. Then to this matrix, we apply the singular value decomposition to filter noise. So the original signal was the measurements here in blue, and after the process, you get the clean values in black. And then the next step was to use the dynamical mode decomposition, which is a technique which is very well known in the computational fluid dynamics community. And this provides this composition of the time-dependent solution as a combination of modes that only depend on space and some coefficients that depend on time, okay? And then the idea was to process these modes that only depend on space by using the topological derivative. Okay, so I'm going to skip the details because I'm running out of time. But after computing this new indicator function, what you can see is what we can obtain at different planes of the form set equal constant. So this first image corresponds to this size of the plate. So the plate where all my defects are carved. And in the next plots means that we are looking different planes going from the green size to the part of the plate which is close to the table. And you can see that at the beginning, the largest negative values are obtained in this plane, meaning that we have defects here. But at some planes, we get almost no blue colors, meaning that the defects are not holes, are only just curves. And by keeping the largest negative values, you can observe that we were able not only to identify the plane reconstruction as normal and standard thermography does, but we were able to identify the correct shape, the correct three-dimensional shape, okay? This is my reconstruction in black of the true geometry when I keep a constant equal to 0.8. And it's also important that the method is robust in terms of this parameter. So if I slightly change this parameter, then the reconstructions are very close. So you can see here the trespassing hole, which is identified as a trespassing hole, and all the other defects are identified as they are, as only carved in the plate, okay? So just to conclude, I hope I have given you an overview about the use of these kind of techniques based on topological derivative computations, and also to make you visualize that is a very, very powerful tool in many different areas of interest. So we can think in acoustic, in electromagnetism, in thermography, as I showed you, but also in many other applications that have been investigated by some other groups, like cardiac electrophysiology or electrical impedance tomography. We have shown that this technique is very good approximation of the number size allocation of the objects, and that in case of having multi-frequency data, then the method can produce very sharp reconstruction. And we have also visualized a little bit about that. This method can be combined with some other techniques to produce better reconstruction just by using them as initial guesses for some more sophisticated iterative methods. And finally, I want to emphasize that this technique is very powerful, not only for, let's say, model problems, but also for real experimental problems and problems related with industrial applications. Okay, and thank you very much.
Okay, thank you very much, Maria Luisa, for this wonderful talk. So let's ask the audience if they have any questions. So please, you can use your microphones or also chat. Okay, are there any questions? So just I don't know if I well understood. John is saying no le deja poner cámara ni chat. Juan. En chat sí te vemos.
Yes, yes.
Ah,
Now
okay.
is open audio and video.
Okay,
No,
John,
can
please.
this,
Okay.
yes, can I ask something? Yes,
Yeah, sure.
Yes. Hello, Maria Luisa. Thank you for your interesting talk. There is a lot of information here and a lot of work, I suppose. Yes, and only one thing, in order to confirm or not, if I have understood well, when you have defined in the mathematical part of the definition of the topological derivative, you have redefined that in terms of the shape derivative, no? I think. Maria Luisa?
Yes.
Yes.
Well, indeed, no, it's not defined in terms of the shape derivative, but you can use an equivalent definition in terms of shape derivative. So this
Yes.
means that you can use the shape derivative to obtain a formula for the topological derivative.
Yes.
It's just one way to find this expression.
Yes, and the reason why you do that, to use the shape derivative, is to have more possibilities to compute that and for reconstruction.
Yes.
And that's the
Yes.
reason, no?
Yes, that is.
That
Is
is
that
the
because
reason.
the formula is not practical. So if you so if you look at the
Yes.
here, if you look at the definition, if you want to implement this on a computer, as I did to show you all my images, this means that for each point you should take a sequence of balls, then evaluate the functional, then compare with the functional without any object, and then compute some limits. So at this point you need to evaluate a lot of times the cost functional. So this is not practical. You need something that you can implement on a computer. Okay. And a very nice way to find a closed form formula, a formula that you can implement, like the one here, which says that I just need to evaluate some function, is to introduce this alternative relation between shape and topological derivative. But it is just a way to find a function that is, let's say, easy.
Yes.
So it's easier to compute shape derivatives than to compute the topological derivative using the definition.
And it helps also in the reconstruction process, no?
Yeah. It's just for the reconstruction process.
Okay, thank you, Maria Luisa.
Thank you.
Okay, are there other questions? So just I wanted to ask you for how about the implementation of these techniques in the case of evolution problems? So can you apply this? Where the EDP, so where you have a partial differential equation, evolution kind?
Yeah, the method is not limited to...
No, okay.
Yeah, for instance, in my last example, it was used for the heat equation. So it does not need to be a stationary problem, or you just don't need an elliptic or parabolic problem. It does not depend. So depending on the problem, you have a different cost functional. Okay, for instance, in stationary problems, I'm using this kind, let's say here. So I'm using this kind of functional and just computing the difference at the receptor. But if you have measurements at different times, then you can compute what's the error at all the times where you measure.
Okay, so just compute some integrals of the solution.
Yeah, exactly.
Okay.
And if you use the formula when you consider all the evolution time, then what you need to solve is a direct problem without any object. In the end, in the formula, what I expect to find is a formula that involves the evaluation of the evolution process in a medium without any object, and also an adjoint problem in which you should solve the evolution problem backwards. So you start at the final time and you go backwards until the initial time.
Okay, thanks. So I think if there are no other questions, we thank you again for give this wonderful talk. Okay.
Thank you. Thank you very much.